Welcome to The Debate. Today, we are wrestling with a really foundational question in scientific discovery. When we push theoretical physics past the current limits of our labs, into realms like quantum gravity or deep space cosmology, what should really be our guide? Should theory be primarily driven by the internal logic, the consistency, and, well, the sheer beauty of mathematical frameworks? My position is that mathematics actually captures the deepest, most elegant structure of the universe itself. So when empirical evidence is scarce, mathematical elegance isn't some kind of luxury. It's the most reliable compass we have to guide theoretical progress toward a unified understanding of reality.
I see why you'd think that, and I definitely acknowledge the compelling history of mathematical success. But I come at it from a fundamentally different angle. Mathematical elegance, while yes, incredibly seductive, is ultimately an insufficient measure of physical truth. I mean, for any theory to remain credible, and indeed to be considered science, rather than just, say, philosophy, it must adhere strictly to the traditional scientific constraint, the principle of falsifiability. We simply have to subordinate elegance to empirical verification. If a theory cannot be tested, if it fundamentally cannot be proven wrong, then it's unmoored from reality, regardless of how beautiful its equations might look on paper.
The history of successful scientific revolutions, it strongly validates what the physicist Eugene Wigner famously called the unreasonable effectiveness of mathematics in the natural sciences. It's not just a descriptive language, it seems to be prescriptive almost. Consider Noether's theorem. It's a purely mathematical statement, right? It shows that for every continuous symmetry we find in a physical system, say if the laws of physics don't change over time, there must be a corresponding physical conservation law, like energy conservation. The math isn't just describing the physics after the fact. The math is generating the core physical principle. And think also of Einstein developing general relativity. He didn't invent the tools he needed to describe curved spacetime from scratch. He explicitly reached for existing, quite abstract mathematical concepts, non-Euclidean geometry and tensor calculus, that mathematicians had really been playing with for their own intellectual merit. This, to me, shows that mathematics anticipates reality. So, in the current vacuum of data for high-energy physics, we really must trust the internal consistency of the math to lead us forward.
Right. I acknowledge the power of mathematical symmetry, like with Noether's theorem, that's undeniable. But we must be extremely careful not to conflate mathematical truth with physical truth. They're different things. Mathematical truths are derived from axioms. They're absolute, but only within their formal system. Physical truths, however, are contingent. They're provisional, always sort of waiting for the next experiment to potentially upend them. That philosophical distinction, I think, makes mathematics by itself an inadequate primary guide for reality. If we rely solely on elegance, we risk physics becoming, as some have said, a seductive prison of pure speculation, where we end up chasing beautiful formalisms that simply have no physical counterpart. I mean, mathematical formalism often permits structures that are physically nonsensical.
Think of tachyons, these hypothetical particles the math allows for, but which seem to violate causality by traveling faster than light. The math permits them, sure, but reality seems to reject them. For a theory to be truly scientific, it has to offer testable predictions, capable of falsification. That's what Karl Popper insisted on, and I think he was right.
Okay, if the goal is testable predictions, then let's tackle the biggest target in the room, string theory. I defend string theory not just as mathematically elegant, but perhaps as necessary. Right now, it's basically the only theoretical framework we have that seems capable of unifying general relativity, the physics of the very large, and quantum mechanics, the physics of the very small. These are two frameworks that are incredibly successful and mathematically coherent on their own, but they violently reject unification when you try to put them together. Now, string theory achieves this unification, but, and this is key,
Only by demanding specific, incredibly complex geometric structures, these Calabi-Yau manifolds, and requiring 10 or even 11 dimensions just to maintain mathematical consistency. That requirement, to me, isn't a weakness. It's potential proof that the math is digging deeper into nature's actual structure than our current experiments can possibly reach. The sheer mathematical fertility of the theory, the way it keeps generating insights, justifies pursuing it, even if the relevant data is currently elusive, way down at the Planck scale.
But aren't you, by saying that, setting up a massive challenge for physics itself? The empirical elusiveness of string theory highlights the exact crisis we are debating here. You claim the theory's consistency is its strength, but that same consistency leads directly to the notorious landscape problem. The string theory equations apparently are so accommodating that they allow for this vast ensemble of solutions, potentially 10 to the 500 different possible universes, each with different physical constants. I mean, if the math dictates that virtually any universe is possible, it severely undermines the whole goal of finding a unique predictive theory of everything, doesn't it? A theory that accommodates anything risks explaining, well, nothing specific about why our particular universe is the way it is. It might be a brilliant mathematical exercise, I grant you that, but without constraint from reality, it's just speculation.
And if we spend decades and billions of dollars on theories that are essentially unfalsifiable by definition, are we really doing science? Or are we just practicing a kind of intellectual faith?
I'm not quite convinced by that line of reasoning, because I think you're confusing the current limitations of the math, maybe our understanding of it, with a fundamental failure of the methodology itself. We aren't abandoning falsifiability altogether. We are merely arguing for the necessary pursuit of mathematically coherent frameworks until our technology, our experimental reach, can catch up. I mean, if string theory is currently the only mathematically coherent avenue we see towards unification, aren't we sort of logically compelled to pursue it?
But mathematical logic, fails spectacularly sometimes when confronted with actual data. Let's look at, say, two specific instances where mathematical consistency just did not translate into physical truth. The first one is pretty basic, from classical mechanics. If you mathematically idealize an electron as a perfect point charge, the equations predict that the electron has infinite energy density. Now, this result is mathematically consistent within that classical framework, but it's physically absurd, obviously. And even more striking, I think, is the cosmological constant problem. Our best mathematical description of particle physics, quantum field theory, predicts the energy density of empty space, what we call the vacuum energy. Okay, so when we calculate this mathematically consistent result, the predicted vacuum energy is approximately 10 to the 120 times larger than what we actually observe in the universe through cosmology.
Right.
That's not just slightly wrong, it's catastrophically wrong. I mean, if the math were truly naively correct there, the universe would have either instantly collapsed or ripped itself apart immediately after the Big Bang. It's almost existential proof that mere consistency, even from our most robust and tested theories, does not guarantee physical truth. The universe just isn't playing by those mathematical rules, apparently.
I absolutely agree that the 10-12 discrepancy is, well, it's staggering. It is arguably the single biggest failure of predictive mathematical physics we've ever encountered. But I see those so-called failures not as a reason to abandon mathematical guidance, but actually as necessary, sometimes violent boundaries that ultimately drive innovation. Those breakdowns, historically, they force the development of new mathematics and entirely new physical frameworks. When classical theory predicted infinite energy for point particles, that pathology didn't invalidate the use of math. It forced the invention of quantum fields theory and techniques like renormalization, which is essentially a mathematical procedure, a human effort, to subtract away those infinities to get results that match observations. Similarly, the cosmological constant problem is, yes, a problem, but it's also an opportunity. It signals a profound conceptual gap that demands we develop a more sophisticated mathematical formalism, perhaps one that incorporates gravity correctly at the quantum level. The physical requirements of planetary motion forced Newton to invent calculus. The need to describe space-time curvature drove Einstein to use tensor calculus. When mathematics breaks down like this, it's telling us we need to develop better tools, not to abandon the toolkit altogether.
That is a fair reframing.
that these mathematical gaps force innovation. I can see that. But it still circles back to the core philosophical question that really underpins our whole debate. Why should abstract mathematics be so incredibly effective in describing nature in the first place? When you place that much faith in the elegance of the math, even when the data disagrees so spectacularly, like with the cosmological constant, you seem to be supporting the idea that the universe is fundamentally mathematical.
Well, yes, that's exactly what I support, or at least lean heavily towards. The success of mathematical language isn't just some happy coincidence, some useful trick we stumbled upon. It seems to be evidence that we are discovering pre-existing objective truths about reality. I lean towards a form of mathematical realism, perhaps even something like Max Tegmark's mathematical universe hypothesis, which posits that physical reality itself is a mathematical structure. The implication is profound. These structures exist independently of human minds, and when we find an elegant equation, we are simply uncovering the universe's own inherent beautiful code.
See, I just don't buy that level of ontological commitment. I really don't. I argue for a much more pragmatic, instrumental view. Mathematics is a highly sophisticated human invention, an incredibly powerful modeling language we developed, because it turns out to be extremely effective at organizing patterns we observe and making predictions about them. Our success in physics shows the immense utility of this tool, absolutely, but not, I think, that reality is fundamentally some kind of mathematical object existing independently out there. I mean, think about the history of geometry itself. Mathematicians made choices, like whether to accept or reject Euclid's parallel postulate. These choices led to different, internally consistent, equally valid mathematical universes: Euclidean, hyperbolic, elliptic geometry. The choice of axioms creates the mathematical system. That variability proves that convention and human choice play a crucial role.
We select and refine the mathematical structures that best seem to match our observations, but the match is always an approximation, a model. The mathematics is a brilliant tool, maybe the best tool we have, but it is not a perfect Platonic reflection of the cosmos itself. Yet that tool, that language born from abstract human thought, has managed to predict things like antimatter, electromagnetic waves, even gravitational waves, sometimes decades before our instruments could ever possibly register them. To just dismiss that predictive power as mere happy invention or just a useful tool, it seems intellectually insufficient to me. And yet that same tool, as we've discussed, predicted infinities that required rather ad hoc conceptual fixes, and vacuum energies that were off by a factor so large it almost strains credulity. We have to admit the tension here remains unresolved.
Indeed it does. I think we've clearly established the profound tension we're dealing with. I maintain that mathematical rigor offers necessary constraints and deep guidance, especially when we're exploring the frontiers of fundamental physics. It reflects, I believe, a profound synergy between abstract thought and the actual structure of the cosmos.
And my conviction remains steadfast that theoretical exploration must always, ultimately, maintain its tether to empirical reality. While mathematics is invaluable, absolutely essential, we must exercise extreme caution. Mathematical elegance, however appealing, can too easily obscure physical truth, making experimental verification and the fundamental capacity for falsifiability the ultimate non-negotiable requirement for generating genuine scientific knowledge.
And perhaps it is precisely this creative tension, this ongoing dance between the abstract language of mathematics and the concrete necessity of observation that actually generates our most profound scientific insights. We invite you, our listeners, to continue exploring the materials and deciding for yourselves which lens provides the clearest view of reality.